Okay. So now we want to show the range is a subspace of W. Yeah, let me get that. So obviously, because W is a vector space, so you know, sorry. We know like V is a vector space. So 0, V obviously is in V. So based on, we already know that, right? So we know like 0 W is in range of L. Okay, so that's the first thing. Okay, based on the same fact here. And then, okay, if V is in range L, then according to the definition, it means there exists, another vector U in V such that LU equal to V, right? Yeah. And we need to show AV is also in range L. We need to show this. This is what we want to show. But we know that, okay, if LU equal to V, then AU, which is, because if U equal to V, obviously AU is in V as well, right? According to because V is a vector space. So AU is in V, and then LAU is going to be ALU, which is A times V. Okay, so that means what? That means AV, that means AV is in range L. Okay, because you can find something that is in V such that like through L it will map to AV. Okay, so that's so we are able to show, okay, range L is a subspace of W. Okay. Okay. So now, okay, here we are trying to, show that LV equal to AV is a linear transformation from R3 to R2. Okay, let A to be 2 by 3 matrix, and V is in R3. So this is so let me erase this. Actually, it doesn't matter, okay? We can make it even more general, okay? That AB M times N matrix Okay, then AX, okay, equal to B, okay, is a linear transformation from Rn to Rm. Okay, because X is n-dimensional. Okay, because we have n number of columns, and B is m-dimensional. Okay, so this is a more general case. So how do we show something is a linear transformation? We need to show L A U plus B V equal to A L U plus B L V, right? That's how we show something is a linear transformation, right? Then, you know, so A times AU plus BV. Here, of course, U and V are vectors in Rn, okay? Are vector in Rn. So then with that equal to, you know, A times AU plus B, A times BV, and equal to, you know, lowercase a, you can get that out. AU plus BAV, right? And this is basically, okay, equal to, well, that's pretty much what we have. No, because this one is this one, and this one is this one, right? This is based on the matrix multiplication property, right? Okay, so if that's the case, obviously, for a 2 by 3 matrix, okay, this is obviously the case. Okay, so find a kernel, okay, you know that and the range of L for the following A. Okay. So first, kernel means AX equal to 0, right? We need to find all the solution of X to make AX equal to 0, right? Right? So that's like something we need to do, okay? So this is a null space of this matrix, right? It's a null space, right? So if it's null space, well, you just try to solve it, you know. Let me get more space. This is 1, -2. One, -2, and then what? 2, 5, and 3, 4. So we can do like elementary row operation to get like multiply the first row by 2 and add to the second row. Something like this, right? And then, you know, we just, you know, continue. Doesn't look good, but you get the idea. Multiply the second row by -2, add to the first row. So this is 3 minus okay, and we know like ax equal to 0, and this one has the same solution, right? So let's just use x, y, z. So we know like x plus 9, 7, z equal to 0, and we have like y plus 9, 10, z equal to 0. So in other words, if we make z equal to t, okay, so x equal to y equal to, so we can represent the whole thing as t times so this is our null space. This is A, something like that, right? So that's like or this is the kernel. Because they represent the same thing. And for the range basically is just like you know, whatever linear combination you can get from the column vectors will be the, what should I say, like your range. Okay, so we can because like we want to get like the space that is generated by the column vectors. So we can do something that is similar to like a basic row, elementary row operation. Let's do elementary column operations. Okay, because it will not change our column space, right? So first we multiply the first column by -2 and add to the second row. Multiply the first row by -3, add to the third first column by -3, add to the third column. Okay, so it becomes 1, -2, and -2 is 0, and this one will become what? -2 is 4, 4, 5, 9. And then, okay, -3, 0, and the -3 is a 6, so it's 10. Okay, so obviously, like you know, we can make it like a 1, -2, 0, 1, 0, 1, and then we continue to do the elementary row operation. Column operation, sorry. So multiply this one by -1, and add to the third one, it becomes like a 0, 1, 0. And then this is -2. If you want, you can do like something similar to Gaussian-Jordan elimination to get this one done. So basically, it will be, so your range will be R squared. OK， 你们知道我在做什么哦？不知道，有人摇头了，完蛋了。OK， 就我现在要保持 current， 我现在是要把 current vector span 出来嘛，对不对 ？span 出来，所以我现在要看说怎么样子可以把它简化一下。简化的话，你记不记得我们做 elementary row operation 的时候，我们保持 row space 一样，对不对？那我们现在做 elementary column operations， 其实是类似的嘛。那我们会保持 column space 一样，对不对？对，只是方向转一个90度嘛，对不对？对不对？所以我们现在就是把这个的后面这边都去掉，就变这样子嘛。那这个就除掉，就变成这样子嘛，对不对？就是我们把这个乘上，就这个 column 乘上1/9，这个 column 乘上1/10就变这样子。然后我们把这个东西再乘上-1加过去，就变这样子。那当然你也可以把这个东西乘上一个2，再加到这个去，就变成这样子，对不对？那所以说，也就是说，你的 column space 展开来，这边 column space 展开来跟这个 column space 展开应该是一样的，对不对？对，那这个摊就是这个很显然是 R square 嘛，对，就是 R2 嘛，所以这个是 range， 这是 range of L，OK。Now exercise prove that A is an n times n matrix, then LV equal to AV is a linear transformation Rn to Rn, and the dimension kernel A plus dimension range A equal to n。这个其实呢 ，this one 我们前面已经证明过，这是一个 linear transformation， 对不对？我们刚刚就是不是证那个 special case 嘛，我就证 n times n 嘛。那再来这个东西 ，kernel A 其实就是它的 null space 的 dimension， 或者叫 nullity， 对不对？就是那个 A 的那个 nullity， 对不对？那这个东西，我们刚刚在做什么东西？我们是不是在做它的 column space 的 dimension？ 那我们前不是讲过吗 ？column space dimension 跟 row space dimension 是一样的，对不对？ The column space dimension and the row space dimension are the same, right? Okay, and it will be rank, right? It is defined as the rank of A, right? And we know like the nullity plus rank equal to n, right? So this one we already proved earlier, but it's just like previously we were using different terminologies. Okay, now we are using something new terminologies, but basically, I mean, it's similar. It's similar. 好不好？这边其实很简单哦，只不过你如果前面的了解，那这边其实很简单。好，那这个就是我刚在做的啦，所以我就不细讲了。所以这个我刚做了嘛，对，所以就。 那 range 就是，对啊，这个我刚刚已经也做了。好，那这个 section 1就结束了哦。那我们就开始讲 section 2哦 ，matrix representation of linear transformations。我们今天可能这个 section 可能讲不完哦，但是就像我like what I said, okay. We should be able to finish this chapter next time and then move on to chapter 5. Okay, like next time. When I say next time, I mean like the week after next, because we don't have class next week. Okay, 下礼拜我们没有课哦。 其实这个学期我们这个课还取消的蛮多的哦。就是说，一方面是因为台风，一方面是因为这个运动会。那好像一方面我也有 conference 出国嘛，对不对？那 conference 出国，我那时候上次有还给你们嘛，对不对？就是我有没有补课？还没补。对，我到时候那个学期末会补一堂课还给你们 ，OK， 补一堂课还给你们，对。好 ，Anyway， 好 ，So actually, all the linear transformations can be written as a matrix. Okay, assume V and W are respectively n and n dimension vector space. Okay, and the B1 and the B2, okay, are the respectively bases of V and W. Okay, if we have linear transformation from V to W, okay, then LV B2 equal to AV B1 with AJ blah blah blah. Okay, this AJ means like a column vector is like the you map VJ. What is VJ? VJ is the basis in B1. Okay, into you write the basis in B1 as using the basis in B2. Okay, you use base of B1 after the transformation. You write it into a basis of B2, and whatever you get, for those coefficient. Okay, that's you use that coefficient as like a column vector, and which form a matrix. Okay, this matrix is called the matrix representation of L with respect to ordered basis B1 and B2. It looks complicated, but actually it's really not that complicated. Just like I said previously, okay, any linear transformation can be represented by a matrix. Okay, so this give you first we have to prove that. Okay, so assume, okay, VB1. Okay, this is one of the vector in B1. Okay, is written as C1. C1, C2, blah blah blah, Cn. Oh, sorry. This is a vector in V. Okay, a vector in V is written using the basis of B1. So it's a C1, C2, blah, 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 Cn. So in other words, V equal to C1, V1 plus C2, V2, blah, 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 plus Cn, Vn. We have that. Assume we have that. For any vector, okay, in V, obviously we can represent it by the basis of V, right? So this is how we do it, okay? That the C1, C2 is just the coordinates of the V, okay, with respect to the basis Vi, okay? And the LVB2 will be, okay, you just transform this thing, right? The V is just this one, right? So, and B2, okay, so you try to transform this into, because it's a linear transformation, so you can expand like this. And you can get C1, C2, blah, blah, blah out. So it's a LV1, B2, LV2, B2, and so on. Okay, so if this can be written, the LV1 can be written as A1. Okay, it means like a coordinate of LV1. Okay, under the basis B2. Okay, and this is the coordinate of the for the LV2. Okay, using the basis of B2. So it represents as A2. So if it's like this, remember each of these is a column vector. So this according to definition, this is basically A. This A, remember this A is this A is this is A1, this is A2, AN. Yeah. So this is our A times C1, C2, Cn. Okay, this is according to the matrix, multiplication, like definition, right? So basically, it just tells you that any linear transformation between two dimensions of finite of two vector space of finite dimensions. Okay, you can use a matrix to represent this linear transformation. Okay, so let's try to look at, see one example. We know this is a linear transformation. Of course, we have to show this is a linear transformation. You can try. Okay, how to show this is a linear transformation? You know how to do that, right? AU plus BV, right? And you put this one into the L. It should be the same as A times LU plus B times LV, right? You can check it out by yourself. But I'm out of time, so I would just assume that we guys know like this is a linear transformation. But this is obviously from two-dimensional to two-dimensional, right? Two-dimensional to two-dimensional. So if you want to use like say the first base is we use like what should I say, like a standard basis. Okay, so it's E1, E2. This is a standard basis for for like R square, right? Okay, so E1 is E10, right? 10. So after transformation, it becomes 2,4, right? 2,4. So it becomes like a 2E1 plus 4E2, right? Okay, and LE2, okay, 0,1. So it becomes 3 negative 5. It becomes 3E1 minus 5E2. Okay, and because this is from R squared to R squared, right? So we can choose the basis such that these two bases are the same because they are both R squared, right? They are both R squared. So we can use the same basis. In this case, we use E1, E2 as B1 and the B2. Okay, so we just put the 2, 4 as the first column, 3, negative 5 as the second column. So this linear transformation can be represented as this matrix multiply xy. Okay, and in this particular example, the B1, B2 are the same. Okay, they are just standard basis for like R square. 就是标准的那个 basis，OK， 就是那个二维空间上标准的 basis。OK， 应该这还可以很容易吧 ？OK， 那我们开始看一些不一样 basis 的，甚至不一样 dimension 的，好不好 ？OK， 就看一些例子。好，这是另外一个啊，就是说这个比较复杂。this one is like a differential operation. Remember, we talk about like a differential operation is also linear transformation, right? We talk about that. Okay, and we have to confine the, U, V and the W to a finite dimension, right? To the finite dimension. Otherwise, if they are not finite dimension, we have problem, right? We have problem because the matrix, okay, has to be m times n, right? Where m and n each represent like a dimension of v and w, right? So the v and w implicitly means like they have to be finite dimensional, right? Okay, so here, okay, take a look, okay, because we confine our space from P2 to P1. Okay, P2, what is P2? It's all polynomials up to the order of 2, right? All the polynomial up to order of 2. And P1 just all the polynomial up to the order of 1, right? And B1 obviously is can be the basis for P2, right? Okay, any polynomial of order 2 or less can be represented by a linear combination of B1, right? Similarly, any polynomial of order 1 or lower can be represented as a linear combination of B2, right? So now let's do it this way, okay? So first, okay, the differentiation, okay, operation on the 1, 0, 0. This 1, 0, 0 means what? Means x squared, right? X squared after the differentiation is 2x, right? Any question? Anyone with like 你们微积分大一修过嘛？对不对？微分都会嘛？对不对 ？x 平方等于2x 这没有问题，没有问题吧 ？OK。So 2x, remember like this, we map the polynomial from P2 to P1. So this one, okay, will be mapped to P1. So this, we have to represent this one by the basis of like for P1, which is B2. So it's so 2, 0, right? Okay. So the other one, okay. 0, 1, 0, so it means x, right? So if you differentiate it, it's 1, right? So by using like the basis B2 is 0, 1, right? And the third one, okay, 0, 0, 1, that means just a constant 1, right? Constant 1, if you differentiate it, it's 0. So it will be 0, 0 using the basis 2. So we can, in other words, we can represent this linear transformation like this, okay? 2, 0 is from there. 0, 1 from there. And the 0, 0 from this third column from here, okay? So we put this as D, B1, B2, okay? From the basis B1 to basis B2, okay? From basis B1 to basis B2. So far so good, right? Okay, let's look at some more example. So this is like from second, like R squared to like R3, right? To R3. Okay. So we want to represent it by this linear transformation by matrix. Okay. Again. So here, okay. Again, we try to use the standard basis. Okay, so LE1 is L10. Okay, it becomes like this. So for we use the standard basis for R squared. We use the standard basis for R3. Okay, so this one is like a 2E1 plus 3E2 plus negative 7E3. And if you use like a 0, 1, it becomes negative 2, 4, 0. So it's like this. So in other words, we can represent this linear transformation by this one. The first column comes from there. The second column comes from here. Okay, and remember, this is from R2 to R3. Okay, from R2 to R3. Okay. So, so far, all the bases we have used are standard bases, right? So now we would like to see an example of non-standard bases. Okay. The first, so this one is we transform from R2 to R3, right? Okay. And for this R2, we use standard basis. But for this R3, we use this, non-standard basis. Okay, you can verify this is a basis. Okay, and basically you just try to do a linear combination of them equal to 0 and see if you can get any a solution other than 0, 0, 0. Okay, you can easily verify it has to be. No, the 3 coefficient must be 0 in order to make the whole linear combination to be 0. Okay, I will not go into the detail of that, but you can check by yourself. So first we put the E1 there. Okay, it's 1, 0, it's 2, 3, negative 7. Okay, so this one can be represented by this one. Negative 5, this one. Minus 2, this one. Plus 7, this one. Yeah, each of these takes some time to compute, okay? Because you need to solve the linear system of linear equations to get the coordinates for from the B2, right? So it takes some time, some effort, I know. Yeah, but well, because we only have 5 minutes left, so I just hand wave this part. But in reality, you have to solve system of linear equation to get this negative 5, negative 2, 7, okay? So it's not so easy to get that. So it's like negative 5, negative 2, 7, B2, okay? So similarly, okay, you plug in E2, you get this one, okay? And again, another system of linear equation to solve. You will get negative 2, 2, 0. So it's something like this. So, so this linear transformation can be represented as this one. And remember, this is from B1 to B2, okay? Where B1 is R2, B2 is 3-dimensional. Okay, you have 3 components. You have 3 components. Okay? So now, okay, we have like a B3 and B4. It's reversed, okay, because here this linear transformation transform R square, a vector in R square to vector in R cube, okay, R cube, R3, okay, and for the B3, okay, which is like the basis for R square, we use this one. B4, this time we use like a standard basis. Okay, so you plug in like a 1, 1, the first first vector in the basis B3, or you get like this one, and this is obviously 0 E1 plus 7 E2 minus 7 E3. Okay, and the second vector from B3, okay, you plug in here, okay, use a linear transformation, you get this one, so it's negative 4 E1 plus E2 plus 7 E3. So this linear transformation from B3 to B4, from B3 to B4, okay, is represented as 0, 7, negative 7, minus 4, 1, 7. This matrix. Okay, and you can put a vector in B3 to get something that is represented as a basis in the basis B4. in R square, okay, or like you know, yeah. Anyway, you get the idea. So far so good, right? So now it's like the most complicated one, okay? Because we the previous example, either we use a standard basis, both standard basis, or we use at least one of them to be standard basis. This one, both bases are non-standard, right? Both bases are non-standard. Okay, we map R square, R cube, R square, like a vector to R cube. Okay, and then for the R square we use this basis B3, and for R cube we use this B2. This B2 has been used previously, right? This is B2, B3. We use B3 here. We use B2. Sorry. B2 here. Okay, so we have used these two non-standard bases previously. It's just like now we put them together in one example. Okay, so we put like the first vector, column vector in B3 into the linear transformation. We get this one, and again we have to solve a system linear equation to get the you know, the coordinates, okay, of the I mean negative 7, 0, 7, okay. You know, of like the coordinate of like using like the basis of B2, and similarly, okay, if you plug in the second column vector in B3 there, okay, you get negative 4, 1, 7. Again, you solve the system linear equation, you get a coordinate 3, 4, negative 7, okay, with respect to the basis of B2. So you put the like negative 7, 0, 7 here, and you put like a 3, 4, negative 7 here, okay, and this is like you know, from B3 you convert it into B2 basis. So this is like the matrix, okay, from B3 to B2. Okay. So one thing that is interesting is that, okay, this one, okay, you convert a vector from B3, using B3 basis, okay, to the using the basis B2, okay, and this is like this is actually the same linear transformation, by the way. This is B3, B2. This one. This is like 2x minus 2y, 3x plus 4y, negative 7x. You can see we actually, okay, always use the same, we always try to talk about the same linear transformation. You see 2x minus 2y, 3x plus 4y, negative 7x. This one, 2x minus 2y, 3x plus 4y, negative 7x. They are all the same linear transformation. It's just the bases are different, right? The bases are different. So, okay, here, if you convert from basis 3 to basis 2, okay, this is like we talk about like a coordinate transformation. Remember, we talk about coordinate transformation, like in previous chapter, right? I mean, if you use one basis, you can transform. You can use the matrix to basically like capture like a change of basis from one basis to another. So this one represent like if you change basis from B3 to B1. Okay, it's this one. And this one is from B1 to B4 using that, I mean representing that the same linear transformation. You can see B1 to B4 using the same linear transformation. B1 to B4. Do we have that? B1 to B. Yeah, we don't have that. But you can try to do it again. Okay, you can for the same linear transformation. Okay, now it's from like B1, which is a standard basis, right, to B4, which is a non-standard one. But you can try, and you will find that this is like a, well, because like a B1, B4. What is B4? B4 is also standard, right? So B1 is standard, B4 is also standard. So that's, you see, that's 2x minus 2y, 3x plus 4y, and negative 7x. So you can see. What happened? It's not working. Here, okay, it's 2x minus 2y, 3x minus 4y, and the negative 7x. That's just this one, okay? Because I mean, it's a standard basis, two standard bases. So it's just a, this is just a simple linear, representation of linear transformation. I think we talked about this earlier. Okay, similar. Okay, and then okay, so this is a basis change. This is like a a linear transformation. I mean, represented by the, how should I say, the from a basis 1 to basis 4. Okay, and then this is a this is a linear transformation. This is like a basis change from basis 2 to basis 4. But here we use the inverse. So with the inverse, it becomes like the basis transformation from basis 4 to basis 2. Okay, so let me repeat. This is from basis 3 to basis 1, and then it's from basis 1 to basis 4, right? I mean, representing that the linear transformation, and then from basis 1 to from basis 4 to basis 2, right? So combined together, it will be this linear transformation from basis 3 to basis 2, right? You can check, you can verify the multiplication of these three matrices will be exactly that. Okay? This is the transition matrix from B4 to B2. This looks like from B2 to B4, but we have a negative 1. This is the inverse. Okay, so be very careful. Okay, so this is like consistent. Okay, so to be exact, we have something like here, like this here. Okay, sorry, give me like 1 more minute. Okay, so it's like we have different vector space. One is V, one is W, right? So you map from V to W, okay, using like L. This is a linear transformation from B1 to B2. Okay, where B1 is the basis for V, B2 is the basis for W. Okay, and then if you have another basis for V, B3, you have another basis for W, B4. Okay, this one represents the the transition matrix from basis B1 to basis B3. Remember, these both represent like a vector space V. Okay, and obviously the inverse is a transition matrix from B3 to B1, right? And this one is similarly, this is from W to W. So it's a transition matrix from B2 to B4. This is transition matrix from B4 to B2, or the other way around. So then, okay, in between, we have this linear transformation. Okay, so for example, this from B1, okay, to the linear transformation from B1 to B2 can be represented by this matrix, okay, T B1, B3, multiplied, okay, on the left-hand side by LB3, B4, okay, and then multiplied by, again, on the left-hand side by the transition matrix from B4 to B2. So you basically, it's just like this one is, you just make a circle, but you are doing the same thing. If you are doing the same thing, obviously they should be the same, right? They should be the same. So all these, like, you know, if you multiply the matrix together, they will be the same. Okay? So try to understand this, you know, figure. This is very, very important. Okay? Later on, we have another figure similar to this one. Okay? If you understand this one, it will help you to understand the other one. Okay? So that's it for today. Okay? I think like we couldn't finish this section, but I will finish up to this transition matrix. Okay? So I will not cover because this one, like we have some like the proof and like application. This application is a little bit irrelevant, and then we are done with this section. So so I think we will cover the quiz will cover up to part of the section 2. Part of section 2, not complete the section 2. Okay, but anyway, I will give you the practice question. Okay, so please try to, you know, practice the questions up to this slide. Okay, and I will see you next week. Not the week after next. I'm sorry. Okay, thank you. 还有记得啊。